to have you all here at the seminar and to introduce our speaker, Zoe Leinhardt. Zoe Leinhardt is an expert in modeling collisions. I was told to keep it short and very modest, so I will just give you an overview over her CV. She did her master's at the University of Washington, where she met, for example, Joachim, then moved with her supervisor, Derek Richardson, to the University of Maryland, where she did her PhD. From that on, she had a postdoc in Harvard, where she met Sarah Stewart, which is another heavyweight in the field that initiated, I would say, a very productive collaboration, resulting in several extremely well cited and well recognized papers on collisions. After that, she had a national fellowship in Cambridge, and then with an advanced fellowship moved to the University of Bristol, where she is currently a professor and head of the astrophysics team. I hope that was short enough. I will leave the floor to you, and I'm looking forward to your talk.
Thank you. Thanks very much for having me, everybody. And please feel free to interrupt me if I haven't clarified something you don't understand. So today I would like to talk to you a bit about some work that we've started doing. I have been working on collisions for a very, very long time. Now I have moved from sort of smaller planetesimal size collisions of kilometer scale objects into giant impacts. And today I'd like to talk a bit about looking for those signatures observationally and connecting them to what we think happens from our numerical simulations. The majority of this talk is going to be sort of one story, but there's lots of work that we're doing sort of around that story. But I sort of thought I'd try and find something that maybe not everyone knew about, because lots of experts in this audience. Okay. Okay. So our solar system, just to give you a brief overview, this is the way that I think about our solar system. It's not so much that I don't think that you know this, it's just the way trying to get you into the way that I'm thinking about things. So our solar system is fairly organized. It has terrestrial rocky planets, so Mercury, Venus, Earth, Mars. Those have solid surfaces. We have gas giant planets, Jupiter and Saturn. Those are the most massive planets, and they're similar in composition to the sun, as far as I'm concerned. They're dominated by hydrogen and helium. Then we have the ice giants, Uranus and Neptune. Those have a thick outer layer of water, ammonia, methane, ice. So basically, they are volatile rich. They have atmospheres of hydrogen and helium and rocky Earth-sized cores as far as we know. We have two belts of smaller bodies, the asteroid belt, which sits between Mars and Jupiter, and the Kuiper belt, which is beyond Neptune. All orbit the sun in a coplanar disk and in the same sense as the spin of the sun. Our sun is standard. It's a standard adult star, main sequence. It is powered by a thermonuclear fusion reactor at its core and converts hydrogen to helium, and it accounts for most of the mass of the solar system. So for a very long time, we assumed that if there were other solar systems, they would look like this. We could not have been more wrong. So let me just sort of really reiterate this point, because I think it is generally important. Okay, so here is another way to look at our solar system. Here we have semi-major axis versus mass. I'm sure you've seen this kind of a plot lots and lots of times. I've put our solar system on this plot, and it is organized by distance from the sun and the composition. So we have the terrestrial planets that are fairly close to the sun, and so they are warm and they don't have significant volatile atmospheres. Then we have the ice giants, which are dominated by volatiles. Those are materials that would boil off very easily. And sorry, I was circling the wrong thing. So gas giants, and then we have our ice giants. And both of these have a lot of volatile elements. And they are farther away from the sun, cooler, and that's where the volatile elements could have condensed initially and can stay bound to those planets. So what is an extrasolar planet really? These are the planets in our own solar system. What about planets outside of our solar system? So these are defined as objects that are less massive than stars. That's not very helpful. They are less than 13 times the mass of Jupiter, which is the limiting mass to fuse deuterium into helium, basically, assuming that you don't have a lot of pollution, or whatever, from other things. The objects have to be massive enough to have reached hydrostatic equilibrium. So they have to be able to round themselves, overcome gravity. Overcome other forces and make themselves spheroidal due to gravity. They have to have cleared their neighborhood of like-sized objects. That, for example, is what Pluto has not managed to do. Of course, we can't really check that. At the moment, we don't have observations that get down to masses of Pluto, so it's not an issue. But it will be. We will not be able to tell if we're really talking about a planet or whatever we want to call Pluto, which we've decided is not a planet. Okay, whatever. That's another whole set of arguments. Okay, and it has to orbit a star other than the sun. This is also important. It could be orbiting a star or a stellar remnant like a pulsar. Those are both legit. But if it's a free-floating planet and fulfills all of the other criteria, it is not an extrasolar planet, because we cannot be sure that it formed from the debris around a star. It could have been a really tiny object that formed like a normal star does. Crap. Okay, so now we're getting lots of confusing things, right? So an extrasolar planet has to be orbiting something, preferably something that's going through thermonuclear fusion or did, and it needs to have enough gravity to make itself basically spherical. Okay, everybody agrees, great. Okay, so now let's look to see what we have actually found. We found a lot, 5,000 at least. And they've been detected by radial velocity, transit method, direct detection, gravitational microlensing, pulsar timing. These colors indicate orbital period, and the gray are objects that we don't have a good orbit for, so we don't have an orbital period for them. And they vary, right? From orbits of 1/5 of a day to 40,000 days. And they also are diverse in mass, in age, in the stellar type of their parent star, in the distance to the star, in the number of planets in the system. They do not look like our solar system, right? At all. So none look like our solar system yet. You notice that this whole region here is vacant. That isn't because there aren't any planets there. That is because it is very hard for us to observe that area. We are constantly pushing, but if I put our solar system on this plot, you can see that we're just skirting the edge of what we can really observe. And there's just an extreme diversity of planets. A lot of them sit in this middle group here. We have objects that are very massive and very close to the star, so hot Jupiters. We've got objects in the middle here, which we really call super Earths, but that's also a fairly vague term. It basically means everything that's more massive than the Earth and significantly less massive than Jupiter. And then you have to, I've plotted up to maybe more than I should have. Maybe some of these objects are really, brown dwarfs as opposed to planets. Okay. So if we look at some of the most different and most interesting extrasolar planetary systems that we have detected, we've got the solar system up here for comparison, which is nice and organized by the type of planet. We've got the terrestrial planets grouped really nicely, basically sitting around 1 AU. Then we've got our gas giants. That's where we would have the most material. So we'd have both the condensation of volatiles and we'd have still significant solid material. So we get the biggest objects sort of right where we would have ice, water ice condensing in our traditional condensation sequence of the accretion disk around the star. And then we've got our ice giants fairly far away from the sun. Now, if we compare on the same scale, some of the most famous extrasolar planetary systems, we've got 51 PEG-B, that was the first planet detected around a main sequence star. That is a Jupiter mass planet that is very close to its star, within our orbit of Mercury, if we were to put it on the same sort of scale. We've got Corot 7, so that has a terrestrial planet that is sitting at an orbit of 0.8 days. And then we've got a super Earth that's right next to it with an orbit of 3 days. We just don't have anything like this in our solar system. And that means that whatever model we come up with for planet formation, it has to explain all of this. When we started working on planet formation, we thought we needed to form our solar system. Nice, organized, well-spaced, well-behaved system. And then we found things that were really, really different. And now our model has to explain all of it, right? And it has to be able to form planets relatively easily, because we think that planets form around basically every star. 1 in 4, is basically close to 100% as far as I'm concerned, right? Yeah, it's less than an order of magnitude. So it's 1, yes, agreed, good. I'm an astronomer, kind of. Anyway, so planet formation. We must form our solar system and everything else. Initially, we assumed that all of the other planets looked like our solar system and they were organized. So we had dense, refractory dominated planets close to the central star, and we moved very reasonably out to volatile dominated planets sort of as we moved out to the Kuiper belt. Extrasolar planets include hot Jupiters. They have not formed where they are found. They had to have formed somewhere else and moved. That is the only way that that will work. So that has significant migration, not something that we've seen even in our solar system, not something that we've seen in our solar system either. And then we've got planets around stars and, So planets form around stars and stars form in molecular clouds. That we still agree on, and still this will work for that. Planets generally orbit in the same sense of their host star. Good. So at least those two things have not been totally messed up by our observations. Young stars have gas and dust orbiting around them in accretion disks, and we've observed that and detected that. But planet formation itself takes hundreds of millions of years, we think. And that we can't really observe dynamically. In fact, it's worse than that. We are only really observing the beginning bit, so these accretion disks. Oh, sorry. We're only really observing the accretion disks and the actual planets that they have formed. The middle bit, that is basically unobservable. At least it has been. And that's where we're really trying to push it. We're really trying to find that middle bit, observational evidence of the middle bit, to make sure that our models that are being tied to the end result have some intermediate steps that we also can tie to. So if we look at a molecular cloud, let's take this beautiful picture of Orion, of the Orion Nebula. And we zoom in and look very, very closely. We can see accretion disks. So these are proplyds And here you can really see an accretion disk that's been, so this is a disk of dust and gas, and the bright bit is dust that's being illuminated by another star. And the dark bits that you can sometimes see, so right here, that is a dust disk that is blocking the photons from the young star in the center. So if we put that information together with what we have from our own solar system, we've come up with a fairly basic story of planet formation. So we start with some dust. Here we have an interplanetary dust particle that's sort of my best guess at the dust that condenses in the protoplanetary disks. And we think that, so microns to centimeters sized of dust, complicated in shape, will be complicated in, its dynamics will be complicated in the protoplanetary disk of gas. And that grows to planetesimals, meter to kilometer sized objects. Here we have the asteroid Dimorphos, which was involved in a very exciting set of craziness last year from DART. But this is really what we would think a planetesimal would look like. And then we get to protoplanets, which are 1,000-kilometer plus sized objects. So they are now spheroidal and have enough self-gravity to overcome any material strength. And I'm just showing the moon as an example. And then eventually we get to planets, Mars to Jupiter sized objects. How we get from the dust to the planetesimals and the planetesimals to the protoplanets is one of the most complicated. And there are several different ideas for how you might get to planets, depending on exactly where you are in your accretion disk and with respect to the central star and what physics dominates. So I'm not going to worry about that bit because eventually you do get to planets. But I would really like to know at the moment what happens between the protoplanets and the mature planets. That's sort of the last phase of planet formation before you get to planets. So if we can sort of work backwards that way, so we've got the initial condition, we've got the final condition, and we're going to hone in on the whole middle story. And I'm going to start by pushing back from the end. And this is my general cartoon of the previous pictures that I've shown. So that beautiful sort of wispy molecular cloud, I have denoted as a sphere that has a little bit of angular momentum. And those sort of crazy proplates that only one of which I think that you could see looked like really like a disk that was edge on. I've decided they're all disks and they're all coplanar and they are behaving well. Okay, so this is sort of a very simplified cartoon of what I think happens during planet formation. And I would like to focus on this last stage, these largest final impacts. So what's the evidence for really large impacts? We've got a bunch of evidence in our own solar system. And we've got some evidence outside of our solar system. So within our solar system, we have a couple of weird things, each of which might have another explanation. But if you put them all together, it sort of suggests that we've had several large impacts in our own solar system's formation. First is Mercury. Mercury has a significantly higher density, mass density, bulk density than you would expect for a planet of its mass, suggesting that it has a higher iron fraction than you would expect. So it has a larger core than you would expect. So it is missing a crust. And there are a couple of ways to do that, but one of them is to hit it hard after it's been made. After it's been built, hit it hard, remove the crust. Earth moon. The best explanation for our moon is a giant impact. Exactly what kind of giant impact there are discussions about and arguments about, but the moon is isotopically identical to the Earth. So that's very hard to explain in any other way, except that the two objects hit each other, mixed well, and you ended up with a satellite. In order for the satellite to be as big as it is, it would have to be a very big impact. And then we've got Pluto and Charon, which sit in the Kuiper belt. And they too are odd in that Charon is quite massive in comparison to Pluto. And it can be formed by a giant impact. Not necessarily needs to be, but could be. And then there are several other objects in the Kuiper belt which have had significant impacts. So evidence for giant impacts in our solar system, at least one, probably half a dozen, right? Outside of the solar system, we also have tantalizing clues that there have been very significant impacts. One is Kepler 107c. So this Kepler system is a main sequence star, 1.2 solar masses, and it has 4 planets, all above Earth mass. So all between a few Earth masses and 10 Earth masses. Kepler 107b, this one, is the one that is closest to the star. Kepler 107c has about the same radius, almost identical radius, but it's at least 2.5 times more massive. So Kepler 107b has a mass density of about 5 grams per cubic centimeter, and Kepler 107c has a mass density of 12. Okay, that is very weird. It is very hard to explain Kepler 107c without a giant impact. It is a massive planet. It should definitely have an atmosphere. It doesn't. And the innermost planet does. So it is hard to explain how you would get the next planet along without an atmosphere from stellar processes if you've maintained the composition of the innermost planet. So the easiest thing to do is to hit it. I wouldn't say that's easy. It takes an incredibly large impact to remove that much mass from a planet that is several Earth masses. But it could be done. Okay. And then we also have super Mercuries, just a few. So these are planets that are like 107c, but they are the innermost planet. So 107c is listed here, and this is from Leinhardt's fantastic paper from 2022. So we have 107c listed here because it is considered a super Mercury, but what I mean is a planet that is the innermost planet, and it also has very high density. Composition like what Mercury would be if it was that massive. And what you really want to look at is this iron fraction column here, which varies between sort of 0.5 and 0.8, where our iron core fraction for the Earth is more like 0.35. So these guys all look like something has happened to them. Maybe they haven't all had a giant impact, but a good fraction of them could have had a giant impact, and that would explain their high iron core fraction. Maybe all of them have. There's only a handful of these guys out of the 5,000 plus planets that have been detected. And then there's another little piece of evidence, which is that there are a couple of these very strange infrared excesses that are seen around stars that seem to increase in infrared excess. So there is an infrared excess suggesting dust around the star. And then there are increases in that every now and then. They're sort of misbehaving. And there are only a few of them. And these are considered extreme debris disks often, so they have very high emission. in the mid-infrared, but there are only a few of them. Again, these are all sort of very indirect pieces of evidence that there are collisions going on, but we're missing the collision. We're even missing really clearly detecting the dust after this massive collision. And if we look at numerical simulations, we would certainly think that you should be able to detect the dust. So when we model planet formation, we have lots of giant impacts in our numerical simulations. And you would produce dust in those, and those dust is very observable. Infrared excess is one of the easiest things to see, from radiation from the star. And that brings me to the main point of the talk, the one impact that we think we have caught. So detecting the invisible. So do I really only have 10 minutes? No. Oh, good. I have 20 minutes. Yes. Okay. Great. Thanks. I'll stop rushing. Okay. Okay. So Assassin 21QJ. How many of you have heard of Assassin 21QJ? Excellent. Okay. Okay. So totally normal main sequence star. Looks like our sun. Chugging along, 2018, it started being a bit weird. Okay. So it is totally normal. It is relatively young, we think. It is very, very hard to age this star, but based on its spin, we believe it is about 300 million years. We also have some spectra of the star, and we believe it still has some lithium in it. So it is young. In comparison, our sun, just for those that might not have this at the tip of their head, it's 4.6 billion years old. Okay. So this star has a rotation period of about 4 days, and our sun has a rotation period of 28 days. And the stars spin down due to magnetic braking. So it makes sense that this one is a bit young. It is an adult star. It's not like a T-Tauri star or something like that. So totally normal, not doing anything weird. Okay. Now I show you the infrared in 2 different wavelengths from 2014 to 2023. So marching along, everything's totally fine, and then it starts to brighten up. So the red shows 4.5 microns, the blue is 3.8 microns. And the infrared excess basically has become undetectable now, but it lasted for over 1,000 days, having not had any infrared excess beforehand. Okay. The infrared excess is consistent with a constant temperature of 1,000 Kelvin. The intensity drops with time, but the temperature stays constant. Now, I'm going to be careful there. I would say the temperature is consistent with staying constant. You notice that the error bars get significantly larger because there is less to detect. Okay. So this is in a paper that was led by Matt Kenworthy, Simon Locke, and Graham. And my graduate student and I provided some numerical simulations to help explain what's going on. But this, yeah.
So this success that you see in the infrared is within the perfect black body that you just have a low temperature, or do you have a, like I said,
Okay. So the Weiss data is fit well with a black body at 1,000 K. There aren't that many data points, but they're at a good place, right? I mean, that is the star plus 1,000 K black body. So the star on its own is blue, before the brightening, red data points here. After brightening, blue data points. Star plus 1000 black body.
And the dashed line, sorry.
And the dashed line, okay, is a 100K dust from the second bit of the story. Okay, so this is a black body for the dust that we think we're detecting much later, but these yellow triangles are just upper limits. So there's no resolved image, right? All of the light is going into 1 pixel. If it was simply dust radiating the stellar emission, the 1000K would put the dust at 0.1, 0.2 AU. But that's not the end of the story. Towards the tail end, so 2.5 years after you have an infrared excess show up, you have an optical transit that is massive and very noisy. So here we have the optical observation of the star looking totally normal during the period where you had the infrared excess start, right? And then a really significant dip that lasts for a long time, 500 days, and overlaps with the infrared excess, the tail end of that infrared excess. Okay, everybody's sort of like, whoa. Okay, so one explanation is that these two things are simply not connected, right? That you have a totally normal star that all of a sudden has a massive infrared excess for 1,000 days and also has a transit event. Okay, so there is no star that we have detected that has an infrared excess where no excess was detected previously. That falls in this category, mid-infrared excess. So we don't have a step up in infrared excess on any of the extreme debris disks or anything with a star that doesn't have an infrared excess to start with. Now, that may be that we weren't really looking for it, but it is also very, very rare to have a transit event like this. So the likelihood that both of these things happen together is fairly low.
So Ken, sorry.
Yeah, keep going.
Just so we get to the,
Yeah.
the intuition. So
Yeah.
what would be the sizes of dust that you would need and how much mass you would need in the dust to have that?
Yeah, so the size of the dust, so this is the optical transit is wavelength dependent. So the size of the dust is probably submicron. It would have to take up an area of 0.01 AU squared.
Okay, and for the
For the
1000,
infrared?
yeah, for the infrared thing, how much? What should be the size of the dust that would?
I think it's all I think it's consistent.
So it's also like
It's also microns because that was 4.5 microns. So I think it's about micron size. Yeah, but I would say that the
kind of covering the disk of the star.
Yeah.
More or less, right? I mean, comparable to the size of the star.
Oh, absolutely.
Right?
Yes. Bigger.
Yeah.
Yes. Yes, yes, yes. Okay. So just to be super clear, what we're talking about is so these are little transits, right? What I'm showing you here. Here's the disk of the sun. And we've got the International Space Station. And we've also got Mercury. Okay. And what we're talking about is like that. Okay. Okay. So just wanted to be like clear. So just so that you can see that's ISIS. I just think ISS, I just think this is like cool. So I have it in, but whatever. Okay. Okay, so when we are talking about a transit, normally a transit is detected we use this for planet detection all the time. And here's like a planet around a star and it's super well behaved, right? So the planet has a fairly well-defined edge, even if it has an atmosphere. And so when you're getting emission from the star and the planet isn't in front of the disk, then you've got sort of your background emission there that has both the emission from the planet and the emission from the star. And then you've got the planet crossing in front of the star, blocks a bunch of the stellar light, and you've got a disk, and it's very well behaved, and then it comes back out again, right? And the transit that I've shown you is super messy, right? Up and down, but it blocks a huge amount of the light of the star all the time, right? But then it goes up and down. So we know that it's not something as well defined as like this planet, and it lasts way too long too. So it's really long in extent, and it's kind of clumpy, and it's very confusing. I mean, it's just generally really confusing. But we can get nominally the periodicity of the transit the periodicity of the transit tells us where this object is, if we can detect more than one transit event. Okay, so are these events unrelated? If they're unrelated, then the infrared excess would be dust, and it would normally be interpreted as dust absorbing the starlight and re-radiating it, right? So it's getting heated up by the starlight and it gets warm, and that's what you're seeing. You're seeing warm dust. And so the temperature of that tells you exactly where it is. Okay, but that's a problem because we have this massive amount of dust sitting very close to the star for 1,000 days at a constant temperature. So that's really hard to explain. The dust shouldn't stay there by itself. It would have to be regenerated. So you have to have a whole bunch of stuff sitting there making it, hitting like comets or planetesimals hitting each other, and then making a bunch of dust for a long time at 0.1 AU. It is what happens like in our asteroid belts and our Kuiper belts and in exo-Kuiper belts, but nothing like having something quite so close to the star lasting for so long. In this case, the excess is absolutely enormous. It's 4% of the emission from the star. So, and as I said already, the dust would have to take up 0.01 AU squared. So it would have to be refreshed for a long time. The transit would then be a totally separate thing, and you'd have some magic transit object that it happens 900 days later and it's just coincidental, and has to be some other crazy thing going on because it's a super messy, very long-lasting transit. It's very significant. So both the excess and the transit are rare events, and it's not likely that they just happen to be a coincidence. So what could you do? Okay, you could keep the stuff still close to the star and have the transit actually be generated by whatever debris disk has magically appeared. But we still have the problem that we would have to explain why that just happened without any notice. There is a paper that suggests that it is due to just all of a sudden there is a warm debris disk from comets being shot into the inner solar system of this particular planetary system. But why you would get a transit that is so large and be able to maintain it for so long is very, very hard to explain. So we suggest something else. We suggest that this is due to a giant impact, and that the temperature of the infrared excess is actually due to the post-impact body. So the temperature doesn't tell you where the dust is. The post-impact body is large enough that it is actually very hot, and it heats its photosphere enough that it stays at 1,000 Kelvin for 1,000 days. Yes.
So short question. So if this signature was from a planet post-collision,
Yeah.
do we have any way to estimate cooling post-impact, and would it be consistent, with what we observe as like the right ballpark or not? I mean, that might be
So-
a way to.
So that is an excellent question, and we don't have an answer for that, but that is what my large proposal is about. So we tried, but we just don't have good enough theory or good enough numerics to be able to do it. So it's not inconsistent.
It's a good start.
It's a good start, right? But we couldn't be sure it's consistent yet. So what we think is going on is that the impact actually happened beyond 2 AU. And that what you have is instead something like this. So we have a giant impact that happens at T0. And then we end up with a hot remnant and a bunch of material orbiting that hot remnant. Now, when you have a really significant giant impact, and this is all relative, when I say significant, I mean a few to 10 Earth masses or maybe mini Neptunes hitting each other. So bigger than Earth masses, less than gas giants hitting each other. You produce an object right after the impact that is very extended. It's very hot, it has a lot of vapor, and it's very extended. That whole object would be sheared out due to Keplerian shear and take up even more space if the alignment is relatively organized for us. So if this is the Earth, and we're looking through this extended object now, and we still have the hot remnant in the center, and then there is star. Yes.
Sorry to interrupt you, Constantine. We talked about probabilities in
Yeah.
earlier. We said, I mean,
Yeah.
all the other explanations are rather or very unlikely.
Yes. Yes.
The alignment
Oh.
of this, can you
Well,
constrain
no.
that?
So sorry. When I say alignment, I don't mean like it's not a disk.
Okay, okay.
It's not a disk. It's like a thing. Okay. So Simon would have called this a crazy extended synestia. He's backed off of using that word, but okay. So it's a synestia. Okay. It's not a. It is puffier, much puffier than this. So we don't need some special alignment.
Okay, good.
But we do need it to be like we can't be looking, I guess, that way.
But it makes it much more likely.
But it makes me yes.
I have some question. So just to make sure that I understand. So
Yeah.
from T0 to T1000 days, you need, I mean, you assume that this object stayed at 1000 K.
So right. So this is okay. So now we're talking about Simon's area. So apparently that is what would happen. So it's not that the same sized object stays at 1000, but the photosphere would be at the liquid vapor boundary and constantly condensing. But what you would see would stay at 1000 K. Yeah, you can argue with him. Okay. Until it's totally condensed and you don't see it anymore. So his calculations from his moon forming paper suggest that it would have a relatively constant temperature until it's all condensed.
Like as a shock.
Yes. But it doesn't mean that it isn't continually condensing. It is continually condensing, but the hot stuff would stay at 1000 K.
And once I cross these 1000 days, then
Oh,
Then-
so you mean how long would we say that it lasted? Oh, we don't have a precise model for that. We're not trying to,
no, I understand, but just
oh, right,
it's part of the story.
right.
It crosses then, and
Right.
then it stays there. This
Oh,
condensed-
so then all of this is going to, we were hoping that this would last long enough for us to see another transit. I don't think it has.
It's already excluded in the observation.
Mm.
Or not?
I don't know.
But do you have an estimate for the
Orbital period.
Yeah.
So I mean, so this is very loose. So if we use the infrared excess to optical to be, so when the infrared started, which we would have thought was here, to optical, which we thought was there, then that would have placed it at about 2.4 AU. And then we have another very, very sketchy calculation for how far away it could be, and that's about 16 AU. So, yeah, but I think we're pretty confident that it has to be at least 2 AU away for several reasons. One is the observational reason, but also because if you go beyond 2 AU and you have impacts that are larger than a few Earth masses, then the Hill sphere and the Bondi sphere are big enough that you would be able to hold on to both dust and volatile droplets, which is consistent with the observations as well. So all of that suggests slightly more than a couple of Earth masses and volatile richness and a little bit more than 2 AU at least.
These 3 minutes. I mean, we're already in the question session.
That's cool. Good. Okay. So, and in addition, we think this is 1000 K. If we took just terrestrial objects, then we would come up with a temperature more like 2000 K. If you put in a little bit of volatiles, you can reduce that temperature. We don't have models that are precise enough to tell us if we could get to 1000 K. So we think that we're talking about impacts between 2 super Earths, mini Neptunes that have some volatile, significant volatile content, at least 2 AU away. And just to check that we could get something big enough, we did an FH impact with Swift. Now, this is a lower limit on the size because we're resolution limited at low density. So it means that we cannot resolve this blue stuff because Swift has a density floor. So that means that it stops really treating material that is very low density using hydrodynamics. So this is the smallest.
What kind of density does that correspond to this?
The density floor for this one?
Yeah.
I actually don't know.
Okay.
I'm sorry.
No.
So, but this, the lower limit, we got 2000 Earth radii. Yes.
Have you tried to run such simulations in the orbit of a star?
Not yet. You mean, yeah.
Yeah,
Yeah.
because that may look quite different.
Well, yes, I think it'd be shared out and hopefully even better. Yeah. Yes,
Cover a larger area.
it will cover a larger area. Yes.
So in the WISE observations, was there time, could you cover, is there other observations covering T equals 0? Or was it missed somehow? Like, I would expect that when the impact happened.
Yeah,
that you
yeah,
would
no,
have seen-
So the optical ones, the optical covered it and there was nothing there.
So one didn't see directly the impact.
No, well, you saw it in infrared, you saw it in heat, but you didn't
But
see
this
it.
was from the dust, but you would actually get a very bright, potentially a very bright, when the impact actually happens from the actual impact energy. And I'm wondering if anything like that was seen
No,
because of lack of coverage or.
But I guess because you're looking mostly at the star, right? You're looking at the star.
Yeah. Okay.
so, and I don't,
Yeah.
and it couldn't be, yeah, it couldn't be separated from the star in any noticeable way in the optical. And the infrared is good, right? Because the star isn't very bright then. Okay, so I'm almost done. Okay, so that's what we think is happening. And what we really need to do is get a thermal model of the post-impact body. So be able to cool it, be able to have mixing, be able to model the photosphere of the impact body, which we so, and we also need observations of it again. And that we've got to JWST proposals that have been accepted. So we do have more observations. I don't know if we're going to be able to detect anything. So finally, this is just my conclusion. So we have a relatively normal sun-like star with no noticeable variability, and it was detected to have significant infrared excess starting in 2018. That excess lasted for years, and it had a relatively constant temperature of 1000 K. In addition, the infrared excess there was also a substantial transit a bit later, and that was detected in optical wavelengths. And it overlapped with the infrared, with the end of the infrared excess. Either of these events are unrelated, and you've got a normal adult star that's done something really weird. And that's not impossible, okay? Or they are connected, and it may be the very first time that we've actually detected an impact, or as close to impact as one could hope for. So I promised that I would explain why I thought we hadn't detected things before. So the fact that we've detected this one would suggest actually that this happens quite often. The fact that we haven't detected things the way we thought we should be detecting them is, I think, because we're not looking for the right things. This was actually very hard to do. We needed to put WISE data together with optical data. We weren't actually thinking of doing it. It was an observer who was actually an engineer by trade, who was just hanging out and sort of said, "Oh, did you notice that this star that also has like a transit, you know?" And I don't think that we're connecting all of the wavelengths together the way we really need to, and that's a very difficult thing to do. And I don't think we're looking through the infrared observations, looking for the things that we need to be looking for either. So I think we're missing them. I don't think it's that they're not there. Okay, that's it. Thank you very much.
This excellent and very interesting talk. Do we have questions? Shall we start with the junior people?
Yes.
Maybe anybody here has questions?
Well, what would you expect to observe if it actually was a giant impact, or what are you hoping to happen in the next couple of years?
Okay, so what I would love is for us to catch another transit. And then we would definitely know how far away, so we just need one more. And we would have a very much better idea of where it is. I'm concerned that when it stops being hot, it all of a sudden gets cold and is effectively not observable, which is why like this size range is so hard to detect. Because then you would really need like your alignment to be perfect and really see like a proper transit. And this star isn't one that was known for that. So I don't think, yeah, but that's what I'd love.
Yeah, so I was wondering, I'm sure it's not clear, we'll talk about it. I mean, if you ask how many of these particular type of impacts you expect to have, right? That just started from the fact that if it's super is very common, very common. And it's not exactly solar type stuff. There's a solar type stuff, so it's also very common.
Yeah.
So can one get an estimate also from numerical simulations and rough estimate? I will get a magnitude estimate.
I think we could. I think I'd like to know is that from our guesses, this had to have a good amount of volatiles.
Right, so
And so it was actually closer to mini Neptunes. And maybe we wouldn't be able to see it as well if it was the slightly smaller, slightly more common. So I think we need a little bit more information. I think one is that we can't quite constrain. It's a little bit not. But I think there should be a couple. I think we should have missed a couple that we maybe have the data for. Yeah.
Yeah, when you said that the dimming of the stars overlapping with the end of the infrared emission, I was somehow expecting you to tell us that this material got treated on the star. Is it a curious coincidence that they overlap in a way?
No, I think the material is getting accreted onto the planet.
But why would it overlap? Why would those two things coincide?
Oh, just because just because I think that, so it has to have, we do have to have the actual transit happening. So we need the whole object to get between us and the star in order for us to see the transit. But we don't need that to happen in order to see the infrared excess. So we'll see the infrared excess all the time.
Yeah, so but why did it stop at that time?
Oh, it didn't stop. It just, I think it's condensing. I think it's basically switching off.
It's still an odd instance, right? It happens. I mean,
I mean, this is years though. I'm talking like, it doesn't, it's not like that. It's like, yeah. Maybe it's like, I mean, the transit could have, you're right. The transit could have happened. This could all have been shifted up.
yes.
Yes.
Yeah, I just want to say that maybe the thing that is surprising or should be thought about is really that it's I don't think it's such a sharp transition in terms of cooling and in terms of statistics.
Yes,
To me,
fair enough.
if I have to guess, I would say, then, you know, even if you have condensation and
Yes.
so on, it should go from 1,000 to 0, right?
Right, and it doesn't, right? I mean, our error bars are enormous, yeah?
Yeah,
So,
right. So you would expect to see some kind of a
Yes.
continuous.
yes.
And also by the way, so then a question, so when you look at the you know, the influence of the star, another thing that wouldn't I expect to have some kind of distribution of sizes and not just all the dust in micron size?
Oh, I think maybe, we don't know anything about the distribution of sizes. I mean, we have observations of 2 wavelengths from
Okay.
Mars. And then we've got.
So you just see microns, but you don't know if there are other
No,
sizes.
no, and definitely nucleation and the size distribution within this, yes, absolutely. No idea.
Let's get one more finger over the eggs.
Just out of curiosity, in the introduction, when you were showing the hints for the giant impacts in the solar system, was kind of expecting to mention the retrograde relation of Venus or Uranus. Is that still a hint? Or?
So Uranus is, yes, absolutely. Uranus is hard. It's a big planet. But absolutely, sorry.
Oh, okay.
Sorry for your nose,
Yeah. There's nothing to feel. I was just.
That's yeah.
Yeah, I mean, sure. Yes, which is why I said it was like between 3 and half a dozen, right? It could be anywhere between 1 and half a dozen, so at least 1, probably more than that. Yeah, I don't know. Sure, yes.
So shall we?